Classical Mechanics Foundations and Formulations. In this lecture, we delve into the core concepts and mathematical formulations that constitute classical mechanics, the bedrock of theoretical physics. We will cover Newton's laws, deterministic systems, conservation laws, Lagrangian and Hamiltonian dynamics, and much more. First, we have Newton's laws of motion. Newton's laws of motion are the cornerstone of classical mechanics, establishing the relationship between forces and motion of bodies. The first law is about inertia. A body at rest or in uniform motion will remain so unless acted upon by an external force. And Newton's second law is about force and acceleration. The acceleration of a body is proportional to the net force acting on it and inversely proportional to its mass, expressed as F equals ma. And Newton's third law is about action and reaction. For every action, there is an equal and opposite reaction. Next, determinism in classical mechanics. Classical mechanics is deterministic, implying that the future behavior of a system is entirely predictable, given its initial conditions and forces applied. The system's evolution can be precisely described using differential equations. Next, we have conservation laws. Several quantities are conserved in classical mechanics linked directly to the symmetries of the system as formalized in Noether's theorem. Energy is conserved due to time translation symmetry. Linear momentum is conserved due to translational symmetry. Angular momentum is conserved due to rotational symmetry, and charge is conserved due to gauge symmetry. Next, the Lagrangian mechanics. Lagrangian mechanics provides an alternative formulation of classical mechanics, emphasizing the principle of least action. Lagrangian function is defined as L equals T minus V, where T is the kinetic energy and V is the potential energy. And this leads to Euler-Lagrange equations. These describe the motion of the system and are particularly useful for handling complex systems with constraints. The Hamiltonian mechanics. Hamiltonian mechanics is another reformulation of classical mechanics, closely related to the Lagrangian approach. Hamiltonian function is defined as H equals T plus V, representing the total energy of the system. And this leads to Hamilton's equations. These govern the timed evolution of the system and are crucial for transitioning to quantum mechanics and analyzing systems with conserved quantities. The phase space. Phase space is much important in classical mechanics. According to Leonard Susskind, he says that phase space is actually space of states. In Hamiltonian mechanics, the state of a system corresponds to a point in phase space. For example, if we have a coin and the two outcomes head and tail, and this corresponds to a set, and that is the phase space for that coin. In Hamiltonian mechanics, the state of a system is represented as a point in phase space with coordinates given by generalized positions and momenta, and the system evolution is described by a trajectory in phase space governed by Hamilton's equations. This concept is essential for understanding statistical mechanics and ergodic theory. Rigid body dynamics. The study of the motion of solid bodies where the distances between particles remain fixed. And the key concepts are rotational kinematics, moment of inertia, and the dynamics of spinning objects described by the Euler-Lagrange equations for rigid body rotation. Next, we have central force problems. It deals with forces that act along the line joining two bodies, such as gravitational and electrostatic forces. For example, the motion of bodies under central forces is described by Kepler's laws in celestial mechanics, with conservation of angular momentum and energy being crucial. Small oscillations and normal modes. The study of systems near equilibrium, where potential energy is approximated by a quadratic form. The simple harmonic motion exhibited by such systems. Normal modes in multi-particle systems, independent oscillation at characteristic frequencies occurs. Next, the non-inertial reference frames. It describes motion in accelerating or rotating reference frames, necessitating the introduction of fictitious forces. For example, the Coriolis force and centrifugal force are essential for understanding phenomena like Foucault's pendulum and rotating planetary systems. The canonical transformations. Transformations in Hamiltonian mechanics that preserve the form of Hamilton's equations and its applications or simplifying problems, finding conserved quantities, and foundational to classical perturbation theory. Next, we have the perturbation theory. In classical mechanics, we have certain problems that cannot be solved exactly, so we use a method to approximate solutions for problems that cannot be solved exactly. This approach involves expanding solutions in a series and treating small interactions as perturbations to a known solution, and it is widely used in celestial mechanics and studying chaotic systems. Next, the chaos theory. The study of systems that are highly sensitive to initial conditions, leading to unpredictable behavior. Despite deterministic equations, chaos is marked by strange attractors, fractal structures, and the breakdown of traditional perturbative methods. The Hamilton-Jacobi theory. A formulation of classical mechanics that bridges classical and quantum mechanics. Hamilton-Jacobi equations, a first-order partial differential equation providing the principal function or action useful in integrable systems. Next, the relativistic mechanics. It extends the classical mechanics to regimes where special relativity becomes significant, and the key concept are relativistic momentum and energy described by the relation E squared equals P squared C squared plus M squared C4. The celestial mechanics. Classical mechanics applied to the motion of celestial bodies, including the study of orbits, the three-body problem, and the planetary system stability, foundational for understanding the dynamics of planets, moons, and satellites. Fluid dynamics. The study of the motion of fluids and the forces acting on them. The key topics are laminar and turbulent flows, Bernoulli equations, and the Navier-Stokes equations applicable in aerodynamics, hydrodynamics, meteorology, and also in black hole physics, and superrotation. Statistical mechanics. Statistical mechanics deals with systems containing a large number of particles, linking microscopic properties to macroscopic observables. The core concepts are entropy, partition function, and ensemble theory provide connections between individual particles and system-wide properties like temperature and pressure. Analytical mechanics. It encompasses Lagrangian, Hamiltonian, and Hamilton-Jacobi formalisms, offering powerful tools for mechanical systems analysis. This approach emphasizes generalized coordinates and the principle of least action for deriving motion equations, providing a more general framework than Newtonian mechanics. Next, the D'Alembert principle. It reformulates equations of motion using the concept of virtual work, and its statement is the sum of the differences between applied and inertial forces for all virtual displacements in a system in equilibrium is zero. This principle underpins the Lagrangian and Hamiltonian formulations. And last, we have the Poisson brackets, an important mathematical structure in classical mechanics. In Hamiltonian mechanics, Poisson brackets compute the time evolution of dynamical variables. The Poisson bracket of two functions f and g with respect to the base space coordinates is given by f and g in curly brackets equals summation I del f over del qi, where qi is the generalized coordinates, times del g over del pi, where del pi corresponds to conjugate momentum, minus del f by del pi times del g over del qi. And this structure is crucial for the study of symmetries and conservation laws in classical mechanics. Classical mechanics offers a vast and profound framework for understanding the physical world. From planetary motion to fluid dynamics, its mathematical formalisms not only describe mechanical systems, but also lay the groundwork for more advanced theories such as quantum mechanics. In our upcoming lectures, we will transition from classical to quantum mechanics, exploring how these classical concepts evolve in the quantum realm. Thanks for watching.